Hello class, in this video we cover the last section of chapter 3.8 Arguments and Euler diagrams. In this section we are going to use Euler diagrams as tools to test the validity of an argument. In previous video we used the truth table as the tool of testing the validity of an argument, right? This section we are going to learn a new tool, Euler diagram. Euler diagram is named after Euler, knowing it's not pronounced as Euler, is Euler. And we have a brief introduction for the mathematician, and also on our book, we have more information. So Euler diagram is very similar with Venn diagram. The main difference is Venn diagram has a rectangular box representing the universal set, but Euler diagram only have circles. Euler diagrams do not have the boxes, the rectangular boxes. Euler diagrams are just like the Venn diagrams that we use in studying sets. However, we do not enclose the circles inside a rectangle representing a universal set. In these diagrams, circles are used to indicate relationships of premises to conclusions. Very, very important, we need to remember the four types of quantified statements and their Euler diagram expressions. The first type, all A are B. Circle A representing or collection A. Set B representing class B or collection of B. This diagram shows all A are B because A is a proper subset of B, right? All A are B. Second type, no A are B. The two collections are disjoint. No A are B. Number three, some A are B. The two circles overlap, and the dot in the middle, right here, representing the one in A also in B, some A in B, or at least one A is in B, right? At least one A is in B. So the dot representing the at least one A in B. And the last type of quantified statement, some A are not B, so it stresses the dots in A but not in B. Okay? In A but not in B. So stress this dot, this element in A but not in B. So this illustrates some A are not B. There's at least one A, one element in A does not belong to B. So very, very important. Spend time to get familiar with those four diagrams representing the four quantified statements. Do you guys still remember what is a quantified statement? We learned that in previous sections. A statement with all, some, no, or none, right? If the Euler diagram agrees with the conclusion, then the argument is valid. Look at this table. Euler diagrams and arguments. 1. The process, how do we use Euler diagram to test the validity of an argument? Step 1, make an Euler diagram for the first premise. Step 2, make an Euler diagram for the second premise on top of the one for the first premise. Step 3, the argument is valid if and only if every possible diagram illustrates the conclusion of the argument. If even just there's one possible diagram that contradicts the conclusion, then the conclusion is not true in every case, so the argument is invalid. The goal of this procedure is to produce, if possible, a diagram that does not illustrate the argument's conclusion. In other words, the goal of the procedure is to trying to find a counterexample. The purpose of the process is to try to find a counterexample to prove the argument is invalid. Yeah, if there's no such counterexample exists, then the argument is valid. The method of Euler diagrams boils down to determining whether such a diagram is possible. If it is, this serves as a counterexample to the argument's conclusion, and the argument is declared invalid. By contrast, if no such counterexample can be drawn, the argument is valid. Let's look at the examples. Use Euler diagrams to determine whether each argument is valid or invalid. So in this argument, we have two premises, 1, 2, and one conclusion, right? Yeah. Step 1, use a Euler diagram to describe premise 1. All U.S. voters must register. I'm going to use this circle to represent U.S. voters. All the U.S. voters are in that circle. And I'm going to use this circle to represent people who register. So this diagram represents the first premise. All U.S. voters are people who register. Second step, use the Euler diagram to describe the second premise on top of the first diagram. All people who register must be U.S. citizens. So a bigger circle representing U.S. citizens. So people who register are U.S. citizens. So the whole diagram describe both premises of the argument. Let's see, do we have the conclusion in all cases? Does this diagram illustrate in all cases the conclusion will be a result, will occur as a result? So all U.S. voters, all U.S. voters are U.S. citizens. It is correct, right? The smallest circle is inside the biggest circle. Yes, this is valid. Does that make sense? Yeah, U.S. voters are all people who registered. People who registered are all U.S. citizens. So U.S. voters are U.S. citizens because the smallest circle is inside the biggest circle. Two premises. Number 1, all baseball players are athletes. Number 2, all ballet dancers are athletes. This is the conclusion. Okay, so baseball players, athletes. Let's say this is the circle representing all athletes. And this is the circle representing baseball players. So all baseball players are athletes. Premise number 2, all ballet dancers are athletes. So ballet dancer, this small circle, also is inside the circle representing athletes. Can we draw the conclusion that no baseball players are ballet dancers? We can't, because I just showed you the counterexample. Is it possible for those two small circles overlap, right? Yeah, they don't have to overlap. Like this case, they are not overlap. But is it possible they are overlap, right? When they are overlap, that gives us a counterexample to disprove the argument. So the argument is a fallacy, is not valid, invalid, because we found a counterexample. All right. Next, all mathematicians are logical. Yeah, the first type of quantified statements. Let's say the bigger circle are people who are logical, and the smaller circle are mathematicians. All mathematicians are logical. No poems are logical. No poets are logical. So poets, P-O-E-T-S, yeah, poets, people who write poems. No poets are logical. So the circle of poets should be disjoint with the circle people who logic. No poets are logical. Therefore, no poets are mathematicians. This is valid. Okay? This is valid because those two circles are disjoint for sure. Next, all actors are artists. So actors, artists. Michelle is an actor. Let's use the red dot to represent Michelle. Michelle is an actor. Therefore, Michelle is an artist. Yes, it's valid. Because the dot is also in the bigger circle, right? Yeah, because the smaller circle is inside the bigger circle. And the dot fall in the smaller circle. That means the dot also fall in the bigger circle. So Michelle is also an artist. Valid. Some houses have 2 stories. Some houses have air conditioning. So 3 circles. Let's do, this is a circle of houses. This is a circle of things with 2 stories. And this is a circle representing things with ACs. Okay. Some houses have 2 stories. Okay, some houses have 2 stories. Some houses have air conditioning. Okay, some houses have air conditioning. Therefore, some houses with air conditioning. Therefore, some houses with air conditioning have 2 stories. Not necessary, right? As you can see, those 2 circles, they do not overlap. This can be used as a counter example. This is invalid because in this diagram, the 2 circles, things with AC and things with 2 stories, do not overlap. They are disjoint. Okay, and that's the last question. Yeah. So Euler diagram is another tool to test the validity of an argument, but the argument, the premises of the argument, and the conclusion, especially the premises of argument, have to be quantified statements. All right, please feel free to email me if you have any questions. I'll see you in the next video.